All right. So there was a question in chat about when the sample exam will be posted. So the exam, if I recall correctly, is planned for this coming week. So I'll have the sample exam posted in the next couple of days or so. Probably this afternoon. So I think at this point, uh, I pretty much know where we've gotten through at this point. So should be able to uh, make a final decision on what'll be on the exam and post the exam in there or post the sample exam and get all of the stuff for the exam set up, the examity session and all of that set up. So I'll probably try to knock that out this afternoon. So keep an eye out for that. I'll send out an announcement when that's available um, and a little more information about the exam as well. The plan for today, we have a few things slated for today. One is finishing the central limit theorem. We got started on one problem, this SAT scores problem, but we're going to finish up the last part of this problem and then work through one more example. And then we're going to start on chapter 7, where we're shifting gears again a little bit. Chapter 7 and 8 really are kind of working on bringing together these two ideas from chapters 2 and 3, the empirical side, the data-driven side, the real-world side of things, and chapters 4, 5, and 6, the probability side, the like theoretical or mathematical side, bringing those two together and trying to come up with a way that we can make inferences about populations based on samples. So that is our goal for today. Two quotes of the day for today, both kind of related to chess. One by Emanuel Lasker, famous world champion, and one by Grandmaster Maurice Ashley. So the famous Lasker quote is, "When you see a good move, look for a better one." And the Maurice Ashley quote is, "There are three types of trades. So when you exchange one of your pieces for another person's piece, maybe you capture their bishop with your knight, expecting that they're going to recapture your knight, for instance. You're expecting to trade, say, your knight for their bishop." So he says there are three types of trades: forced, fantastic, and foolish. And if it's not forced or fantastic, then it's foolish. So a trade is something that kind of, in a sense, permanently alters the game moving forward. And I think, both of these have the idea that when you're evaluating a move, evaluate it carefully. And the higher the consequence of the move, maybe the more careful the evaluation should be, or maybe the more conservative the evaluation should be. And I think that's something that can be brought to life as well, right? If you're, you know, how much effort you decide to put into, say, one homework set is of less consequence than how much effort you decide to put into studying for a final exam or into, a term paper for an English course or something like that. And that's probably of a bit less consequence than the decision of, what job to take whenever you graduate and you have a couple job offers. Should you go here or there? That's a more consequential decision, especially if it involves, say, moving out of state or something like that, right? So I think that's, that's the impact that this can have on real life, outside of just chess. Okay, so continuing on with the central limit theorem, just reminding ourselves what the central limit theorem says. It says for large n, which we take as a rule of thumb to be sample size at least 30 or coming from a normal population, the sampling distribution of the sample mean, that is the distribution of the random variable x bar, when taken with replacement from a population with mean mu x and standard deviation sigma x, we can say three things about it. One, we can say that mu x bar equals mu x, and that the standard error sigma x bar equals sigma x over root n. Neither of those are super surprising. We basically worked through that in chapter 5. But the really surprising thing is that we get an approximately normal distribution out. So x bar is approximately normally distributed with mean mu x and standard deviation sigma x over root n. The larger our sample size, the lower the standard error in the mean, the less x bar from our sample is likely to bounce around. We would expect the x bar from our sample to be quite close to mu, and to stay quite close to mu for a very large sample size. And recall that the central limit theorem can also apply to p hat, our estimate for probability of an event or probability of success, the binomial parameter. And we worked through two parts of this example last time, so really quickly recapping that. We assume the national average SAT score, math plus verbal, is 1028, and the population standard deviation is known to be 100. For part A, we're making an additional assumption. If the scores are normally distributed, compute the probability X is bigger than 1050. That is, the probability that a single randomly chosen student's score is above 1050. And we saw this was just a basic general normal distributions problem. Probability X bigger than 1050 could be rephrased as probability Z bigger than 0.22. Using symmetry, we could rewrite that as probability Z less than negative 0.22. And a table lookup gave us about 41.3%. For part B, we got rid of the assumption that the scores are normally distributed. They might not be. There might be some skewedness to it or something like that. For B, compute the probability that the average of 30 student scores is above 1050. That is, compute the probability that X bar is bigger than 1050 for a random sample of size 30. And the calculation here looked pretty similar. Probability X bar bigger than 1050 was probability Z bigger than some number. This number was, if I can select the numerator here, this number was the deviation from the mean, 1050 minus 28, or 22 units, divided by a standard error, divided by a standard deviation. But instead of being divided by just 100, it was divided by 100 over root 30. Or that equated to probability Z bigger than 1.2, or probability Z less than negative 1.2. So only an 11.5% chance here. And then lastly, let's compute the probability that the average of 200 student scores is above 1050. So for 200 students, again, n is bigger than or equal to 30, so we can apply the result of the central limit theorem. X bar, the sample mean, is approximately normal, with a mean that's the same as the mean of the underlying data, 1028. And a standard deviation that's the standard deviation of the underlying data, 100, over root n, over root 200. And let's figure out what that is, 100 over root 200. That's about 7.07. We'll call it about 7.1. So probability that X bar bigger than 1050. Well, now we really just have a question about a general normal distribution. We have a distribution of X bar, 1028 in the middle here, 1050 somewhere over here to the right, and we're looking for that area. Should be less than 50%. Not really sure how much less. Let's convert this to a question in Z. So we take the X bar index of interest, 1050, minus the mean of X bar, 1028, divided by sigma X bar, 7.1. So this gives me 22 over, we'll do 7.07, I guess, make it a little more accurate. That gives me about 3.11. So this is the probability that Z is bigger than 3.11. Now I know with my table, I have areas related to Z, which is great, but they're all left tail areas, and I have a right tail area here. I need to flip around. I'll use symmetry to do that. You could also use complementary events if you wanted. So I'll flip everything about this zero axis, this axis of symmetry. The positive 3.11 comes over here to negative 3.11. The right tail area turns into a left tail area. And I see I'm looking for probability Z less than negative 3.11. That matches my negative Z-scores idea and this picture. So I see a Z index of negative 3.1 and 1/100th. That is 0.0009 for that probability. So 0.0009 is pretty close to 0.001, or about 1 in 1,000, about 1/10 of 1%. 11% is maybe like 1 in 9 or something like that. And 41% is like 2 in 5, or 1 in 2.5 or something like that. So why is the probability changing when my so-called maybe anchor point of 1050 is not changing? It's because the standard deviation keeps getting smaller and smaller, the standard error in the mean. It's being divided by root n. So what I have is an axis of symmetry of 1028 that does not change between any of the distributions, a point of interest 1050 that does not change, and for, let's say, n of 1, just for a single sample, or a single individual in the sample, I have a normal distribution. For n equals 30, I have a normal distribution with a smaller variance, which means these tails are smaller and the peak is a little higher. I made that one a little too extreme. Let me try that again. Let me try to start from over here. That hump is a little wonky, but I'm not going to try it again. And then for n equals 200, I have maybe this red curve, smaller standard deviation still. So if I look at the areas to the right, because I'm concentrating more and more mass towards the middle of the distribution, near 1028, the area in this tail off to the right of 1050, because the area to the right of 1050 does not include that center point 1028 where mass is getting concentrated. That tail gets smaller and smaller as the standard deviation shrinks or as the sample size increases. Now, if we were looking at, say probability x bigger than 1020, then as I concentrate more mass near 1028, I would be including that higher concentration of mass near 1028 in the event that I'm interested in. And then my probability would be getting bigger. Right. So we see it's a near impossibility to get 200 student scores randomly chosen, averaging to more than 1050, but it's not unlikely at all to get a single student scoring above 1050, and it's not all that unlikely to get even an average of 30 students scoring above 1050. Okay, let's look at example 2 down here. So example 2, an elevator is rated at 3,125 pounds. This might be like 2,500 pounds plus a 25% safety factor. and it claims a maximum safe occupancy of 16 passengers. Now, if you've ever actually looked at the numbers in an actual elevator, you'll know that the number of passengers that it says it can safely accommodate is almost always larger than the number of people who could fit in there, even if they were packed like sardines. But let's just suppose that this elevator was big enough to actually fit 16 passengers in it. We're going to look at male passengers because as a general population, males are heavier than females. So the kind of worst case scenario would be that we get 16 male passengers on the elevator. We're looking to find the probability that it's overloaded. So kind of the worst case scenario for 16 people on an elevator would be 16 males on an elevator. And we're going to suppose that men have weights that are normally distributed with a mean of 182.9 pounds and a standard deviation of 40.8 pounds. And the question is, if 16 male passengers get on the elevator, what's the probability it's overloaded? Right. We can never really engineer something for like the worst theoretically possible case, right? I mean, you can't engineer an elevator for what if 16, patients from like My 600-Pound Life or something all got on there, or, the 16 heaviest people literally in the world all got on the elevator at the same time. Like, you would have to overbuild things so ridiculously that you could never afford it. So what we're looking at here is, well, if 16 male passengers get on, I mean, they're probably not all going to be 240 pounds, right? Now, we could say, okay, well, if this is an elevator at a construction site or something, well, maybe construction workers tend to be bigger guys, versus if it's an elevator in, an accounting firm or something like that, right? I mean, where people are probably, more kind of average size. So we might want to look at subpopulations like that in some cases, but here we're looking at this distribution and we're saying, well, I mean, if I randomly choose 16 male passengers, chances are that I'll get a couple folks that are a decent bit heavier than normal, maybe up around 210, 220, 230. But I'll probably also get a few folks who are lighter than normal, maybe around 160, 150. And they kind of like balance each other out, right? That's really kind of what's happening in the normal distribution where the standard deviation is going down. It's why we're getting kind of more concentration near the mean. We have a chance of picking somebody who's, say, way off to the right side of the distribution, but the law of large numbers says, and if I pick a decently large sample size, I should also get somebody who kind of far off to the left of the distribution. When I average those folks together, they end up kind of meeting in the middle. So that's the idea here is, it's going to be quite unlikely that I pick 16 male passengers who are like all over 210 pounds. I'm probably going to have, a lot of people near the middle, some people that are a little heavier, some people that are a little lighter. But we want to figure out what's the probability it's overloaded if 16 male passengers get on the elevator. And if we really wanted to follow this up, we could ask what's the probability it's overloaded if, say, 8 male passengers and 8 female passengers get on the elevator, or even a little more complicated, just 8 people or 16 people from the population who could be either male or female following 2 different distributions. So for each person, we have to pick, will they be male or female? And then in their distribution, where would they fall? Right. So you can add layers of complexity to these problems, but we're starting with a simpler problem. All right, so I can approach this in 2 different ways. I can either set up a random variable, we'll call it, maybe I'll call it like x tilde, which is the sum of the 16 guys' weights, and ask, what's the probability x tilde is bigger than 3125? So that's kind of the natural setup from the problem. I could make this work. There's a version of central limit theorem that would apply to sums. I mentioned that last time, but it's a little bit more of a pain to deal with. But I noticed that if I take x tilde over 16, well, that's x bar. And I can ask probability that x bar is bigger than 3125 over 16. That would be the same answer, right? So I could rephrase this in terms of x bar, which works a little more naturally with my central limit theorem as stated above. Okay, so I know that x bar, since the individual's weights are normal, x bar, even though I don't have 30 or more in my sample size, x bar is going to be still normal. I can still apply the conclusion of the central limit theorem because I have a normal underlying population. The mean of x bar is going to be the mean of the underlying population, 182.9. And the standard deviation, sigma x bar, is going to be the standard deviation of the underlying population, 40.8 over root n, or root 16. Well, that's 40.8 over 4. I think that's 10.2 for the standard deviation, or the standard error. So now I just have, I've done the difficult central limit theorem part and the understanding the problem part. Now I just have a question about a normal distribution. I have some random variable, x bar, that's normally distributed with this mean and standard deviation. And I want to know what's the probability that x bar is bigger than 3125 over 16. Or in other words, probability x bar is bigger than, let's figure out what that is, 3125 over 16, 195.3. So here's my x bar distribution, centered at 182.9. I want to know what's the probability x bar is bigger than 195.3. I know this probability should be less than 50%. Should it be a lot less? Should it be like 1%, or is it like 10%, or is it like 40%? Let's see. Again, I want to rephrase this as a problem in Z. So my Z score for the point of interest, 195.3, is 195.3 minus the mean, 182.9, over the standard error, or the standard deviation of x bar, 10.2. And that gives me about 1.22. Be a little careful that if you're going to do this all in one line, you use parentheses around the numerator, or you can do it in 2 lines like this. But that gives me about 1.22. So this is probability that Z is bigger than 1.22, which is probability that, so we use symmetry, we flip everything around. Here's 0. 1.22 flips to negative 1.22, and we now have an area to the left. That's probability Z less than negative 1.22. And I'll come down here, and here's negative 1.2012. So it's about an 11% chance it's overloaded, 11.12%. So if we were to load this up with 16 male passengers, I mean, it's not overwhelmingly likely that it's overloaded, but it's also probably not unlikely. So kind of at a first pass, it looks like we might want to either reduce the number of passengers we claim that it's rated for, or maybe increase the the weight rating, put stronger parts on or something so that it's weighted to 4,000 pounds instead of 3,100 pounds, something like that. Or we might say, well, we kind of did a very, very conservative thing here by assuming that it's 16 male passengers, like the worst case scenario in terms of male versus female passengers. What if we built another layer onto this model? What if we did either 8 male and 8 female passengers? That seems reasonable. Males and females are about 50-50 in the population. Or we could build even another layer onto that, and say just 15 passengers from a general population, where we have this like mixed distribution of two normal distributions, a little bit harder to work with. So, there are a couple routes we could go here. We could just change the engineering on the basis of this, or we could say, okay, I got an initial idea from this model. Now, I don't want to say I got a number that I don't like from my model, so change my model because of that. But, if I had seen that in the worst case scenario, there's only a 1% chance it's overloaded, and I was happy with that, then in a normal case scenario, it's going to be even less likely it's overloaded. So I would be, I could do the simpler model and then be assured that the more realistic scenario is even safer. But since this maybe is above my tolerance, 11% is not unlikely, I could either just say, okay, we'll take this worst case scenario, we'll engineer for the worst case scenario, or I could take this and say, all right, let's put in the extra effort to do a more realistic model and see where the numbers actually fall in a more realistic model. Any questions on this? Okay, any questions on normal distributions, central limit theorem, sampling distributions, anything in chapter 6? As I mentioned last time, the last bit of chapter 6, testing for normality, I've posted that as a supplement on YouTube, so that's on the YouTube playlist. It should be, it's either the last two videos on the playlist, or it's the second to last and third to last, and last class's recording is the last video. So between these, this supplement is posted in 2 parts, and then last class is posted. So those 3 videos should be the last 3 videos on that YouTube playlist. So check that out. Work through the testing for normality, or watch the testing for normality supplement, work through that homework. Let me know if you have any questions. But that wraps up chapter 6. Are there any questions on chapter 6? All right. Oh, and one thing I did want to show you just really quickly, kind of as an aside. So as an aside, we have a normal distribution with a mean and standard deviation and a right tail area. We can actually just ask Excel to give us the number directly. So I just wanted to show you what that would look like. You don't have to use this. This isn't the official way in the course. We're using mainly the calculator and, paper and pencil. But if you wanted to make use of Excel, you certainly could do that. If you type equals, because we're going to ask Excel to compute something with a normal distribution. And if I start typing NORM for normal distribution, I see I've got a couple of things. I've got norm.dist, norm.inverse. I've got a couple others down here. But let me go with norm.dist. Now, X is our index of interest. In this case, I'm just going to put in the actual index of interest. I can even put it in as 3125 over 16. I don't even need to do that computation myself and get the 195.3. I can just put it in this way. What's the mean of the normal distribution I'm dealing with? 182.9, comma, what's its standard deviation? 10.2, or I could even do 40.8 over square root of 16. And do I want it to be cumulative? Well, yes, true. So I'll put true here. I want an area, not just a height of the PDF at this point. Like if I was trying to make a program to graph the PDF, I might say false, and that just gives me a bunch of heights of the PDF or individual densities. That's not what I want. I want a cumulative area here. Now, one thing that I notice is Excel also gives me areas to the left. So this gives me the area to the left of 195.3. So here I'll just use my complementary event rule and do 1 minus. The area to the left gives me the area to the right. And there's my 11 point, well, this here we got 11.12% from the table. We rounded these numbers like 195.3 and 1.22 a little bit. Excel is going to be a little bit more accurate. It's going to do less rounding in each step. But we see that we get roughly 11-ish percent, 11.1-ish percent for our answer. So if you want to use Excel, you could use Excel as well. If one little caution, if you do use Excel, my stat lab might not like it so much because it's kind of expecting you to use the table. But say on an exam or something like that, if I go through and I see that you're that close, then I'm going to give you the full credit for the problem manually. If you're on a homework problem and you use Excel and it's not accepting your answer, shoot me an email and then I can just take a look and if it's just for rounding error like this or rounding differences, then I'll give you full credit. Or if it's something, more fundamental, if you're off by a bit, then I'll let you know that as well. But you can use the equals norm.dist function in Excel to compute normal probabilities. You could also use norm.inverse, where you give a probability, say 0.95, and let's just say 0 and 1 on a standard normal means 0, standard deviation 1. And that's our 1.645, our Z index with 95% area to the left that we probably recognize from a few previous problems. So norm.inverse, you give an area and get out an index. Norm.dist, you give an index and get out an area or probability. Now, you still need to know what you're looking for and how to manipulate these probabilities and so on, because, like I said, you have a naturally a left tail area here. So you need to know, okay, I've got to convert that to a right tail area. I need a 1 minus from the complementary events rule. Or if you wanted, a right tail index for, say, 5% area to the right, I need to know to do, say, 0.05 and then take the negative of that or something like that, or to turn that 5% area to the right into a 95% area to the left. So I still need to know the underlying ideas and principles here. And that's why I didn't introduce doing it with Excel in the first place. But once I know those ideas and principles, Excel can make some of the calculations simpler or go more quickly. Okay. So norm.inv for norm inverse, normal distribution inverse, or norm.dist for just normal distribution. Okay, so moving on to chapter 7 then, chapter 7, confidence intervals. We're going to talk about 3 confidence intervals. I think your book does proportions first. We're going to do proportions second, but we're going to start with confidence interval for the mean when the standard deviation is known, then talk about confidence interval for proportions, and then we might or might not get to this today, confidence interval for the mean when the standard deviation is unknown. So these are the main 3 confidence intervals we're going to talk about. And we'll also discuss a 4th type of confidence interval for variance or standard deviation. That'll be, at least at the surface level, it will look a decent bit different than these 3. These 3 should all, at the surface level, look pretty similar. Okay, so moving on to confidence intervals. Our goal in this section is to say, okay, if I am interested in knowing the population, let's say mean mu, but I don't have access to the population. I have access to a sample. I can compute a sample mean X bar. So I know X bar, I want to know mu. And if somebody asks me, I have a sample, I compute X bar, and they ask me, what's your best guess for mu? I would say my best guess for mu is X bar. But if somebody then asks me, well, how good is that guess, right? If you've ever, taken a physics or chemistry class or something, and you had to do an experiment where you did a bunch of measurements of, say, the same experiment, um, you'll kind of realize that the best guess is only really relevant if we have an idea of how much error there is inherent in that guess. How much can that guess wiggle around? If I am in physics and I take a ball and I put it at the top of a certain ramp and I drop it and I start the timer at the top, stop the timer at the bottom, that gives me a time it took for this ball to traverse this ramp at this angle. And I do that exact same experiment, put the ball in the same place, start the timer, stop it. I'm going to get different times. I mean, it's not because physics changed or something in the meantime. It's just, I'm not super accurate pushing the button on the timer or letting the ball go exactly the same way every time or whatever it may be. So there's going to be some natural error in there. And I want to provide some idea of the amount of error that there is in my best guess. So I want to provide a best guess along with an error, right? A statement of the ball takes, 6 seconds plus or minus 0.01 second to traverse this ramp. That's a very different statement than the ball takes 6 seconds plus or minus 4 seconds, right? So those are two very different statements, even though your best guess of 6 seconds is still the same between the two. So that's our goal here in confidence intervals, to give some idea of the error in our estimate. And we're going to start with building up the confidence interval for the mean when we know the standard deviation, when we know particularly the population standard deviation sigma. So we know that X bar is an estimate of mu. These types of estimates we call a point estimate, a best guess. What's my best guess for mu? It's X bar that I got from some sample data set. So what's an estimator? We have to talk a little bit about what estimators are and also what makes a good estimator. So an estimator is a sample statistic that we use to make some kind of inference about a population parameter. Our estimators typically get the notation where it's the parameter, but with a little hat over top of it. So I have a population parameter theta that's just kind of some parameter. We don't, whatever it may be, whatever aspect of the population we're interested in, we'll call that parameter theta. And it has a sample statistic theta hat that acts as an estimator for it. We've seen this idea before where we have a population parameter P, the binomial proportion, and P hat is the estimator for P. So we've seen this notation before, but we can apply this notation more generally to say an arbitrary parameter theta that we're interested in. So what makes a good estimator? Well, these are some criteria that we choose to impose on our estimators. The first is that expected value of theta hat should be equal to theta. In other words, if I take a random sample, compute my sample statistic, my estimator, I take another random sample, compute my estimator, I do that a bunch of times, I get a bunch of different values for my estimator, and then I average those together, that should be pretty close to my actual population parameter. In other words, if I was interested in the population mean, mu, if I take a sample, compute X bar for that sample, take another random sample, compute a different X bar, another random sample, another X bar, when I average together a bunch of these X bars, the average of them should be quite close to mu. And we saw this before in chapter 5. We computed that the expected value of the random variable X bar is mu. We also kind of were reminded of that in the central limit theorem, mu x bar equals mu. So x bar, for instance, satisfies this unbiased characteristic where the expected value of the estimator is the thing it's estimating. Sometimes this is likened to, like, you have a target, like an archery target, and I have my archer shoot some arrows, and they don't all end up right on the bullseye. But if I look at where the arrows end up and I kind of average them together, the average is right on the bullseye. Not every arrow hits the bullseye exactly, but the arrows kind of on average sometimes are a little to the right, sometimes a little to the left, sometimes a little up, sometimes a little down. But I don't have something like this. Right? This would be like a biased estimator. Well, maybe I'll make it up versus down. Right? This would be like a biased estimator because the average for these arrows is maybe somewhere like up here. It's not at the bullseye. The second criterion we want, this one's a little more technical. We want convergence. In other words, for larger and larger sample sizes, we want to know that our estimator gets closer and closer to the thing that's estimating. This was what our weak law of large numbers said, is that x bar goes to mu as sample size goes to infinity. Note that this isn't the same as 1 exactly. In other words, or an example, I could come up with a silly estimator where maybe I just like know magically what mu is, and I construct an estimator for it that half the time is mu minus 1 and half the time is mu plus 1. Well, hey, that estimator is unbiased. It's unbiased because on average, half the time I get mu minus 1, half the time I get mu plus 1. I'm like, I kind of have a target where I have a whole bunch of arrows that hit here and a whole bunch of arrows that hit here. And on average, they're right on top of the bullseye. But this never converges to mu, right? If my sample size is 10 or 100 or 1,000 or a billion, it doesn't matter. I just kind of randomly choose mu minus 1 or mu plus 1 as my estimate. It never gets closer than 1 to mu. It's always going to be 1 unit away from mu, no matter what my sample size is. So, I mean, that's a silly estimate, but the point is that criterion 1 and criterion 2 might at first glance seem to be the same criterion, just restated, but it's really not the same criterion. Two different ideas. And then the third, this convergence into how quickly our estimator gets close to the population parameter it's estimating. We want it to be the fastest of all of the estimators that satisfy the unbiasedness property. So this is the minimum variance property. We might have a bunch of different estimators that satisfy 1 and 2. We want to choose the one where the convergence into is the fastest, and that's what we call a good estimator. So we have some good estimators that we've encountered already. Well, the one we've been talking about the most, x bar being an estimator of mu, x bar turns out to be a good estimator of mu. Well, that's nice. S squared, our sample standard deviation, when we do the whole dividing by n minus 1 kind of deal, that's a good estimator of sigma squared, of the population variance. P hat, probability of an event or probability of success, the binomial sample probability, is a good estimator of P, the population parameter P, for that probability of that event. So that's kind of nice. Most of the estimators that we've encountered so far are good estimators of the things they're trying to estimate. We do have a really unfortunate thing in that S, the sample standard deviation, even when computed with the n-1 deal in the denominator, and it's technically not a good estimator of sigma. There's something called Jensen's inequality, and when we apply the square root to s squared into sigma squared, because square root is a nonlinear operation, that kind of breaks the good estimator property. So unfortunately, S is not a good estimator of sigma. And for this course, we're going to pretend that S is a good estimator of sigma. We're going to suppose that, we'll give a rule of thumb and say that, okay, for the purposes of this course, S is a good enough estimator of sigma that we're just going to run with it. We're going to build, confidence intervals and things for the standard deviation on the basis of S essentially being a good estimator. Or in other words, we're going to suppose that for our purposes, square rooting anything that we do to the variance gives us an equivalent thing for the standard deviation, and the thing that we get for the standard deviation is, good enough for our purposes. But that is a rule of thumb that is not technically correct. But we're going to, make that assumption for the purposes of this course. There's actually quite a good Wikipedia page on constructing an estimator for the population standard deviation. And if you look at you can just look at the length of the Wikipedia page, which Wikipedia is, a summary to start with, and you can look at the length of that summary of these ideas, and you can tell how complicated of a problem this is, right? This is not something where we can say, oh, just do it a little bit differently, just use a slightly different formula, and then it's a good estimator of sigma. No, it's not a problem that's easy to solve. So it's quite difficult to get a quote good estimator of sigma. So now our natural question is, okay, well, X bar is an estimator of mu. Heck, it's even a good estimator of mu. So if I said, here's some sample data, what's your best estimate of the population mean? Well, you would compute X bar, you'd tell me that, and you'd also be confident that you're not just making something up, but you actually have some argument for saying that X bar is actually your best guess for mu. It's a good estimator of mu. But that still doesn't tell us how good it is. Our best guess could be really good, or it could be really accurate or precise, or our best guess could be really terrible, right? I mean, if you ask me what's my best guess at the Powerball lottery number tomorrow or whatever, I might give you my best guess, but it's probably not going to be very good. Okay, so let's try to give some type of answer to this. How good is our estimate of mu? And the way that we're going to phrase that is through what we call a confidence interval. X bar itself is a point estimate of mu. It's our best guess for mu. Our confidence interval is an interval estimate for mu. What do we mean by that? We mean that we want to report an interval from a lower bound to an upper bound. I want to report an interval from one number to another number. And I want that interval to mean something like my best guess for mu is X bar, and I'm say 95% confident that mu is in the interval L to U, lower bound and upper bound, something like that. So now our question is, how do we compute L and U? Well, one thing that we know is that X bar, our best guess for mu, our point estimate, has, again, under rule of thumb assumptions by the central limit theorem, it has a normal distribution with a known mean and standard deviation, with a mean mu and standard deviation sigma over root n. We also know that X bar is unbiased, so it's not like it's going to typically overshoot or overestimate mu or typically underestimate mu. So it also makes sense for this interval to be symmetric about X bar. So I'm going to impose symmetry. I want my lower bound to be x bar minus some number, and my upper bound to be x bar plus that same number. We call that number E, the margin of error. So here's what I want. I have my distribution of x bar. This is a random variable. It's normally distributed. Its mean is mu, the population mean. I want to come up with a lower bound and an upper bound. That's close enough to symmetric, I think. Each of which is a distance e, or a margin of error, away from mu. Now, I do have one little issue here. I don't actually know what mu is, but my best guess for mu is x bar. So we're going to kind of erase mu and write in x bar. But now I've kind of written x bar in two different places and it means two different things. This x bar is the random variable x bar. And this x bar is like we have a data set and we compute x bar. That's the x bar from our data set. I'm going to give this a name, x bar observed. The observed x bar from the data set. And this is the random variable x bar. So I have two different ideas here. I've got to keep them straight. One is x bar, the random variable that has this normal distribution, a mean, and so on. The other is the idea that I have some data in the empirical world, right? The x bar random variable is like in the chapter 4, 5, 6 world, the theoretical world. The x bar observed is like the chapter 2, 3 world. I have some data, I have a data set that came from a sample, or that is a sample. And I compute x bar, I compute the mean, the sample mean for that data set. That's what I'm calling x bar observed. That's my best guess at what mu is. Now, I did pull a little sleight of hand here where I just swapped mu in for x bar observed. That's not technically a correct thing to do. The technically correct way to do this is to note that mu minus x bar observed has something basically like the same normal distribution as up here and go that route, but that's quite a bit messier. And so we can do it this way and we get the same answer. So I'm cheating a little bit here. For a really precise derivation, we should do this a little bit differently, but this is kind of morally speaking the same thing. So there is a little detail here that I'm brushing over and pulling a little bit of sleight of hand here by just swapping x bar observed in from mu. But I see that L is going to be x bar observed minus a margin of error, and mu is going to be x bar observed plus a margin of error. I know what x bar observed is, right? This is something that I get from my data. So now my problem is figuring out what is the margin of error. If I choose a larger margin of error, L and U get wider, and I encompass a larger proportion of this area under the curve. And if I choose a smaller margin of error, L and U get narrower, and I encompass a smaller proportion of the curve, a smaller area, a smaller probability. So I have a certain confidence level that I need to decide on. Oftentimes we use a 95% confidence level, but we could use 99, we could use 90, we could use something else. 95 is by far the most common, 90 and 99 the next most common. But there's, in theory, not a reason that we couldn't use a 92.5% confidence interval. We just don't usually do that. what is this confidence level saying? It's saying it's the confidence that I have that mu, the true population parameter, is in the interval L to U. So mu could kind of fall anywhere along this normal distribution here, anywhere along minus infinity to infinity. So the only way that I can be 100% certain that I've included mu in my interval is to use the confidence interval minus infinity to infinity. I can have 100% certainty, but I don't really say anything then. So we pick a confidence level that kind of balances the amount of certainty that we have, so we're pretty confident, but we can also make a meaningful statement. Maybe 95% often fits that bill. So let's say that we're interested in a 95% confidence interval. I want to choose L and U so that this area is 95%. In other words, I want to find the middle 95% of the distribution of X bar, the random variable. And we did this before for Z, and I gave it as an exercise to do in the general normal distributions, that coin weight problem. So if I want to find the middle 95%, in other words, I want to give an L and a U that will, where mu will be in that interval L to U 95% of the time, we'll miss 5% of the time. 5% of the time we'll give an interval that doesn't actually contain mu. So we've made an error 5% of the time then. And by the symmetry of everything, half of that time, or 2.5% of the time, we'll kind of miss on the lower end. Mu will be below L. And the other 2.5% of the time, mu will be above U and we'll miss on the other side. So what does that mean? Well, that means that, for instance, U is the 97.5 percentile of X bar. Or that means that if I think about running out of colors here, if I think about the similar question in Z, if I have 2.5% to the right, my Z index is Z subscript 0.025 for 2.5% area to the right. So U is going to be the mean X bar observed plus Z times the standard deviation of X bar. Z 0.025 times standard deviation sigma X bar, or that is sigma X over root n. Well, this must be what E is, the margin of error. If I have a sample, I know what X bar observed is, or I can compute it anyway. I know what n is, that's just the sample size. And by assumption, we're assuming that sigma is known, that we know the population standard deviation. So by assumption, we know what sigma x is as well, and we can compute a z-score. We can compute a z-index with 2.5% area to the right. We can compute everything that we need to find L and U. So to kind of summarize all of this, let me zoom this in a little bit so you can read it a little easier if you're on a small screen. If we want a p% confidence interval for mu, we want the middle p% of the distribution of x bar, our best guess for mu. And here, if we take alpha to be 100 minus p over 100, it's just the area in each tail. Or I'm sorry, the area combined between the two tails. The area in each tail is alpha over 2. And our lower and upper bound are x bar observed plus or minus z alpha over 2 sigma x bar. Or that's x bar observed plus or minus z alpha over 2 times sigma x over root n. Note that this is z subscript alpha over 2, not z alpha divided by 2, or 1/2 of z alpha. The over 2 attaches to the alpha. We have the probability, and then we find the z index. We don't like find the z index for the full probability and then have the z index. The area is what gets halved because we're chopping the remaining area. We have 95% in the middle, 5% outside, and we're chopping that in half to give me 2.5% in each tail. So we have our formula now for computing a confidence interval. And it built right just directly off of our previous work in general normal distributions. It's a little more difficult to follow because it's very abstract. We don't have numbers we're dealing with, but we have all these letters and variables and symbols and so on. But it's really the same idea that we've been dealing with all along. There is one technical detail to mention here, and that's this idea. What I'd really love to say is something like this. My best guess for mu is x bar, and I'm 95% confident that mu is in the interval LDU. Turns out that there's a little bit of a technical issue with that. We're analyzing this from the perspective of frequentist statistics. It turns out in Bayesian statistics, this would be a perfectly fine thing to say, where the interval LDU would be fixed, mu would be taken as a variable, mu would have some distribution imposed on it, and then we could make such a statement without a problem. But in frequentist statistics, what the frequentist would say is, well, mu isn't variable at all. It's a characteristic of the population. It's fixed, we just don't know what it is. So mu isn't random, it's fixed. If we had the whole population, we could just compute it. But we just don't know what it is. What's random is L and U. Why is that? Well, because I compute L and U on the basis of X bar observed, and that comes from the sample that is randomly sampled from the population. That's where the randomness comes in. When I take a sample from the population, that's a random sampling, but the population itself is not random. Its mean is not random. The X bar that I compute once I have the data is not random, but it's the process of getting the data that's random. So it's really this guy that's the random, or that's, let me just say random. That's an instance of a random variable. So that means that L and U are actually the random variables. They actually are the things that have a distribution placed on them. So, stats textbooks make a big deal about this. It's a little bit less of a big deal in confidence intervals in this context. But the kind of analogous idea when we get to hypothesis testing is actually quite a big deal. So for instance, if we made a confidence interval for a particular problem, we said there's a 95% chance U is in this interval, that's probably not going to fundamentally mislead somebody. Somebody's mental model or their understanding is probably not going to be very different than if we said it the proper frequentist way. But if we go to hypothesis testing and we make kind of a similar mistake, if we have a similar misunderstanding in hypothesis testing, then we will actually very substantially mislead ourselves. So, like I mentioned, that's a fundamentally Bayesian statement saying mu is in the interval L to U. So we really should say something like this. The proper way to phrase a statement about a confidence interval is there's something like there's a 95% chance that an interval constructed in this manner or constructed using this process would cover the true population mean mu. It's a little bit of a nuance, and there's a bit of grammar here that's a little tricky, but that's really the proper way to say it. There's a 95% chance that the interval would cover mu, rather than there's a 95% chance that mu is in the interval. So again, pretty minor detail in confidence intervals is not likely to mislead somebody if you say it the wrong way. But in hypothesis testing, if you make a similar misunderstanding, it can be quite misleading. Okay, let's let's just discuss this quickly because it's pretty quick. Let's look at constructing a confidence interval for P given P hat. So recall that P hat is number of successes over number of trials, the binomial estimate for proportion, the binomial sample proportion. And that we said it's a good estimator for P, and that under certain assumptions, specifically that NP is bigger than 5 and N1 minus P is bigger than 5, P hat is going to be normal with a mean of P hat, mean of P hat observed, and a standard deviation of square root of P hat times 1 minus P hat over N. So again, we have this little frustrating thing here where this is a random variable and these are observed. So we're doing a similar kind of sleight of hand to what I did up here. And we can construct a P% confidence interval for little p, the population proportion, the population probability of the event, in a similar manner to what we did for mu. And if we went through those same steps using this normal distribution instead of the one above, we get L to U is L and U, the endpoints of the confidence interval, is P hat plus or minus Z alpha over 2 times the standard error, which is P hat times 1 minus P hat over N. So similar type of confidence interval, we have point estimate plus or minus a margin of error, and the margin of error looks like a Z index times the standard error. Right. This just came right out of the central limit theorem for P hat. Right out of this statement up here. Okay. All right, let's look at a couple examples. So example 1, the administration of a certain hospital would like to know the mean noise level in the hallways. Patients who are recovering, it's good if they can get good sleep and a good amount of rest. So we want to keep the noise levels to a reasonable level. They take a random sample of 84 readings and find a sample mean noise level of 61.2 decibels, assuming that the standard deviation is known. We'll assume the standard deviation is known to be 7.9 decibels, maybe from other studies or something like that. Let's compute the 95% confidence interval for the true mean noise level in the hallways. So what do we know? And what do we not know? Well, we don't know mu. That's the big, the like elephant in the room, right? Is we would like to know mu, the true mean noise level, but we don't know mu. If we did know mu, we would just say, this is the population mean. There's no reason to do point estimates or interval estimates. There's no reason to do any kind of estimate. If I knew mu, I would just tell you what it was, and that's what it is. End of story. No questions asked. But we don't know mu. So what do we know? Well, we know our point estimate. We know X bar observed. of 61.2. We're assuming we know the population standard deviation. We're assuming we know sigma is 7.9. So we don't know mu, we do know sigma. Now, we might ask ourselves, does this seem like a very realistic scenario where I don't know the population mean, but I do know the population standard deviation? Admittedly, not really. We're going to build up, though, to the point where we don't know mu and also don't know sigma. So this is a stepping stone to something maybe a little bit more realistic. But here we're assuming we do know sigma is 7.9. We also know n, the sample size is 84. Oh, I actually have it right here. What do I need for my confidence interval? I need x bar observed. I have that. I need sigma and n. I have those. I also need to compute my z index. That relies on the confidence level. So I do know my confidence level, 95%. Really, the only thing of interest that I don't know is mu. A confidence interval of 95% means that alpha is 5% or alpha over 2 is 2.5%. So I know a bunch of stuff, I just don't know mu. So what's my 95% confidence interval for mu? Well, my lower and upper bounds are going to be x bar observed plus or minus something. My lower bound gets the minus, upper the plus. I need a z number. Let me come back to that. And then I need to multiply by sigma over root n. 7.9 over root 84. So the last thing that I need is z alpha over 2. Or I need z 0.025. In other words, I need the z index. I need the z index with 2.5% area to the right. Well, there's two ways I could think about this. I could think of this as the 97.5 percentile, or I could kind of flip it over and say negative z 0.025 is just the 2.5 percentile. Right. I could either think of this as the 2.5 percentile, giving me negative 1.96, and then just flip that over to the right side, giving me positive 1.96. That's kind of using symmetry, or I can think of this as the 97.5 percentile using complementary events. I could come to the positive z-score side and look up 0.9750. Happens to hit right on, so we see that that's associated with positive 1.96 for z index. Right. Either way, I get 1.96. We should be pretty used to doing these table lookups now. So I just put 1.96 in there. If you're not sure where these numbers are coming from, take a look back, do a little more practice on the standard normal distribution section and the general normal distributions, and that should shore up some of this working with this normal table. Then I need 61.2 minus 1.96 times 7.9 divided by the square root of 84. Does that look right? Looks good. So for the lower bound, that gives me 59.5. And for the upper bound, if I do second enter, that brings up my previous entry, and I can just navigate up to the minus and change it to a plus. I don't have to type everything in again. the upper bound is just the same as the lower bound with the minus swapped to a plus, or vice versa. So 62.9 for the upper bound. So my 95% confidence interval from mu is 59.5 to 62.9 decibels. Or in other words, I'm 95% certain that the interval 59.5 to 62.9 does cover the true mu, the true mean noise level in our hallways. Any questions on that? Now be really careful how you interpret this. This isn't saying that we're like 95% sure that, all mean or all noise levels in our hallways are between 59.5 and 62.9. This is just saying something about the mean, right? A mean of 60 could come from like half the time being 59 and half the time being 61, or a mean of 60 could come from half the time being 40 and half the time being 80, right? So we're not saying something like this interval represents, the range of reasonable noise levels that we've experienced or something like that. We're saying that this range, 59.5 to 62.9, is kind of the range of feasible mu's that we think that our population mean kind of reasonably could be. So this is only saying something about the mean. This is an interval estimate for the mean. Roughly speaking, we're saying that we think that mu is in the interval 59.5 to 62.9, although that's technically not quite correct. Okay, let's look at another example. A company wants to know the average price of novels in the market and assume that prevailing market knowledge suggests that sigma is $3. A sample of size 25 is taken. The sample mean is X bar observed equals $14.50, and we will assume normality of prices. We'd like to construct the 90% confidence interval for mu, the true mean price of a novel. And so again, what do we know versus don't know? We don't know mu. We do know X bar observed, $14.50. We know N, our sample size of 25. We know sigma, population standard deviation of $3. And we know our confidence level of 90%. This tells me that alpha is 10%, or that alpha over 2 is 5%. So my 90% confidence interval for mu, I have a lower bound and an upper bound. They're both based off of X bar observed. So 14.5 plus or minus or plus some Z number. Let me find that in a couple minutes here. Times sigma over root n. So 3 over root 25, or that's 3 over 5. Square root of n, square root of 25 is just 5. I do need to find Z alpha over 2, or Z 0.05. Different confidence level here. So the Z index that we're looking for is different than last time. We are looking for the Z index with 5% area to the right. 5% area to the right, and the right tail, 5% area to the left, and the left tail. That would give us a total of 10% area. That's our kind of total error rate, the total amount of time that we report an interval that does not end up covering the true mean. So 5% area to the right means we have 95% area to the left. Let me look on my positive Z-scores table. for an area or probability of about 0.9500. That's one of my special cases here, between 0.9495 and 9505. I see that corresponds to a z-score of 1.645. So let's use that. I plug both of these in my calculator. That gives me 13.5 or so on the lower bound, and the upper bound is going to be 15.5, right? The margin of error is going to be about 1. So second enter, we can bring up our previous entry, change the minus to a plus, everything else stays the same. And this gives me about $15.5 for my upper bound. What's my 90% confidence interval for mu? 13.5 to 15.5. There's a 90% chance that the interval 13.5 to 15.5 covers the true population mean mu. And of course, a 10% chance that this interval does not cover the true mu. Any questions on any of this? Okay, let's shift gears a little bit and look at a confidence interval for P, the probability of an event. So suppose we roll a 6-sided die 100 times, and we observe 21 ones. So we could get 1 through 6. We kind of expect that if the die was fair, we get like 16.7 ones, but of course, we're never going to get exactly that many ones. So maybe we'd expect to get 16 or 17. We get 21. We want to compute a 95% confidence interval for P, the true probability of rolling a 1 on the die, and then maybe even follow up with a little bit of an educated guess. Does it seem plausible that this die is fair on the basis of this confidence interval? Okay, so remember our confidence interval for P is this here. We have our point estimate P hat observed, plus or minus a margin of error. Our margin of error is a z-score, z alpha over 2, times a standard error, times the sigma x bar, or standard deviation over root n. Root PQ over root n is what this stands for, or what this represents. Okay, so what do I know? And what do I not know? Well, I don't know P, of course, right? P, or the probability of rolling a 1. If I did know that, I wouldn't be going through this, uh, you know, uh, this process of giving you a best guess and an interval estimate and all of this. I would just tell you what P was. So I don't know what P is, but I do know, or at least I can find easily P hat observed. Notice that the standard deviation doesn't explicitly pop up here because the standard deviation of a binomial is just a function of P. So this P hat observed does all the heavy lifting here. It is the point estimate as well as giving the standard deviation information. I know n, of course, my sample size. My n is 100. My p hat observed is number of successes, or number of trials that satisfy the event. Number of ones that came up, that was 21, divided by the number of trials was 100, or 0.21. And I know my confidence level. confidence level of 95% says that alpha, 95% of the time I'm successful, 5% of the time I make an error. Alpha is my error rate, or alpha over 2 is 2.5%. So this is the relevant area for my Z index. So my 95% confidence interval for P, well, I have a lower and upper bound. They're both based off of my point estimate, P hat observed, 0.21, minus or plus a margin of error. And that margin of error is going to be a Z number, a Z index, times the standard error. In this case, the standard error is square root of P hat, 0.21, times 1 minus P hat observed, 0.79, 1 minus 0.21, over N, over 100. And same thing down here. What Z index do I need? I need Z alpha over 2, Z 0.025. I need the Z index with 2.5% area to the right. And again, I could either think of this as the 2.5 percentile and then make the index positive. 2.5 percentile will be a negative number, make it positive, or I could think of it as the 97.5 percentile. The first way would be more like using symmetry. The second way, more like using complementary events. And my 97.5 percentile, if I go the complementary events route, just like before, associates with the Z index of 1.96. Now there's a lot of stuff here, but I'll just type it in my calculator bit by bit. So I have 0.21 minus 1.96 times, all of this goes in the square root, 0.21 times 0.79 divided by 100 and parentheses. I don't need parentheses around the numerator because everything is multiplied there. So that looks good. And this gives me 0.13 or so. For my lower bound, my upper bound, I want basically the same thing, but just with a plus instead of a minus. So I'll do second enter, bring out my previous entry. I'll use my arrow buttons to navigate over to the minus sign and just swap in a plus for that. And that gives me 0.29 or so. My 95% confidence interval for P is 0.13 to 0.29. Or I'm 95% certain that this interval, 13% to 29%, covers the true probability of rolling a 1, P. Does it seem plausible that I is fair? So if the die is fair, then P, or the probability of rolling a 1, is 1/6, or about 17%. And I do see that 17% does fall in this interval. This interval does contain 17%. So 17% is, kind of within the realm of reasonable possibilities for this die. Or in other words, another way of thinking about this is kind of in a perfect world, at least in some sense. If we rolled a die 100 times, we would get like 17 ones. Or at least if we rolled it, 120 times, we would get exactly 20 ones. But there's always going to be a little bit of sampling error. Sometimes I'll roll a couple more ones than other times, even if the die is completely fair, just due to sampling error. Is 21 ones so far away from the kind of expected number of ones, 17, that we would say this is so far away. I don't think it's just due to sampling error. I think that the die is actually unfair. Or is 21 ones kind of close enough to 17 that we say, okay, I mean, we're going to get a little bit of sampling error. This seems well within reason. This sample of 21 ones seems well within reason that we could get based on just sampling error. And the latter, I think, is the case here. We ran the numbers, we got the confidence interval. The confidence interval did include 17%. So this could easily have just occurred by sampling error, getting a few more ones than we might expect. We wouldn't probably want to conclude that a die is unfair on the basis of the sample of getting 21 ones on 100 rolls. Be a little bit careful, just observing that we got 21 ones on 100 rolls isn't sufficient for us to really strongly conclude the die is fair, but we probably wouldn't want to conclude that it's unfair on the basis of this sample. It's still plausible that it's fair, but I haven't given really strong evidence that it's fair. I mean, I might have gotten 57 fives that come up, right? So for one thing, I've only looked at the number of ones that I got and nothing else. Any questions on this problem? Okay. I think since we only have 8 minutes left, 7 minutes left now, I don't think we have time to get through this problem. So we'll maybe leave this for next time and call it a day for today. So let me end the recording.